Okay, here we are. It's the physics video lecture. This is Physics 107B video lecture 1. And I'll just start off with some brief discussion of the syllabus, which I have in front of me. It's just one page. And we're using Griffith's 4th edition, Introduction to Electrodynamics, great book. Okay, so I'll assign homework problems right out of this book for the most part. And chapters 7 to 12 of the text, check my old syllabus, that's how we did it in the past. Let me know if there's something different. But yeah, chapter 7 to 12, which means we're starting out with electrodynamics, moving charges, fields that change in time. Really excellent material. Homework, pictures of the handwritten lecture notes and work problems sent to me every Friday, and I'll just write this down, lecture notes. Lecture notes. That's the first thing, and the second thing is the homework. Pictures to my email, KRUNDE at CSU Fresno EDU. So it'll be 2 sets of pictures, and subject, always open a new email, that's the best. Subject would be Physics 107B notes for the notes, and same thing here, homework for the homework. So 2 sets of pictures every week. New, I wrote that here as well, I believe. New email message every time. Yeah, that works. That works the best. And then we have examinations, one midterm, one final exam. So we just want to get into the subject matter, because all this other stuff can be discussed and discussed some more. So we're doing electrodynamics. So we're chapter 7 of Griffith's Electrodynamics, and the culmination of that chapter is the full set of Maxwell's equations. So we're really building up to it with some phenomenology. So this is electrodynamics. So we could say moving charges and changing fields, changing in time. So time dependence. But we're going to just start, first of all, with Ohm's law. Okay. Ohm's law, in the form that the current density is proportional to a force per charge. So just, vector and a vector proportionality constants, a material property. So let's go ahead and define these things. We've got the current density, and so that would be charge per time, that's a current, and then per unit area. So I'll just write here charge per time per unit area. And then F here is going to be a force per charge. And they're both direct, so they're both vectors. And this is the conductivity. Okay. So that's already something, and if we're thinking about, on the left hand, we're going to be thinking about, say, a constant current density under some circumstances. But then if we're thinking about a constant force, then we actually should be getting an accelerated charge. And yet, if we're having something constant here and something accelerated here, there have to be some kind of collisions at the microscopic level. There have to be, we can think of, there has to be friction so that a force gives you a constant instead of an accelerated type of motion. Oh, I see here also the inverse of the conductivity is the resistivity, and we could just use them interchangeably. Resistivity. Resistivity, there we go. Okay, so there's going to be some kind of collisions here. Let me make a note about this. It's kind of a physical note. On the one hand, we can just take this as a material constant and not worry about it. On the other hand, the idea that if we have a force here, constant acceleration, giving us something constant instead of something accelerated, we have to kind of deal with that. Okay, so I'm just right, constant force typically applies acceleration unless you have some kind of friction. Unless friction is present. And in the case where you have a swarm of electrons drifting around, then the friction, what we're calling friction here, we put it in scare quotes, and the friction is due to collisions. Okay, it's all right. Arrow your collisions of the electrons. And that gives rise to an interesting little calculation that the author does. So let's just have a look at that. Kind of a qualitative thing. That will give us sort of a handle on this conductivity. So we could call this conductivity atomic model. Or microscopic would be better. That's what we're thinking, microscopically. Okay, so we have that swarm of electrons. There's some applied fields, some applied force, and so they're going to move on in some certain direction here. And let's first talk about the applied force. So, applied force is just electromagnetic. So we can just use the Lorentz force idea. So we would have J is equal to sigma, and then the force per unit charge would just be E plus V cross B. So we've got the electrical and the magnetic component. Now, we're going to assume that V is much smaller, or is small, and later on you learn that it's small with respect to the speed of light. Okay, so it's definitely small. And so we can neglect this. V is small, typically. So we're just looking at J equals sigma E. Okay. And now what we want to do is get an idea of these quantities microscopically. So we'll set this up in the following way. I can use the right side of the board. So the first thing is that we suppose there's some drift speed or some thermal speed. So we'll start with a thermal speed that these things have in random motion. So thermal speed of random motion, we'll just call that V thermal. And then we'll assume there is an average separation distance. Average separation of these atoms, of these charges, of these electrons. Average separation lambda, and that gives us time. Okay? We take a length divided by a speed, and that gives us a time between collisions. Okay, so we've got the time between collisions. We're going to keep this list going here, this construction. So they're accelerated like this. So continuing this list here, let me go ahead and erase this. So continuing, we would say the speed, the average speed that they attain by being accelerated would be acceleration times time. You know, constant acceleration, speed, acceleration times time, but because it's the average, it's a half of that. And now we can go in here with our time, lambda over the thermal speed, and then the acceleration, which is F over m. So, can't erase that. So the acceleration would be that F over m, but that F over m would be QE over m. Okay, so that's the average acceleration, and then the time is going to be lambda. Oh, we already have that lambda. So good, QE over m. So the next thing, we're going to assume we have n conduction electrons. Okay, so we have this 5, assume n electrons, so n free electrons per unit volume. And now we can construct this quantity. I'll put this over here. So now we have, for our J, go ahead and give it the vector sign. We've got that N times Q, right? Number per unit volume times Q times V average. Check the units on this, by the way. Number per volume, we've got charge, we've got length per time, so that's actually going to be dimensionally charge per time per area. Okay, so that's right. Keep going. We've got the NQ, we've got the 1/2, the lambda over V thermal, and we've got that F over M, which we already see as QE over M, so that's Q again, E over M. Since it's a vector, it's this vector right here. So now let's just bracket what we have outside of the E and have a quick look at it. Okay. So we have J proportional to E, and remember that was just our sigma. So we have N lambda Q squared 2m V thermal. So this is a really interesting expression just on the qualitative side of things. As said before, for us it's just going to be a material constant, so it's just a number. But its behavior is interesting. We see that it depends on the number of charge carriers, which is the electrons, and depends on this thermal speed, and there's a temperature dependence in here. V thermal, which you know from the ideal gas law, from the kinetic theory of ideal gas, is proportional to the square root of the temperature in Kelvin. So you see you're going to get a smaller value of this as the temperature increases. Okay, good. But again, this is really this thing here, and we're going to leave these considerations as having done them and continue along with that discussion right there. Good. So the first application is just a cylindrical wire. Let me go ahead and send this up. So from now on, we're just taking sigma as a material property, and we're doing a couple of applications. So first of all, we want just a wire, essentially. So we'll just call this an example. So we have some kind of cross section, could be circular. There we go, and we can call this cross section A and length L. And we're going to have a potential across the two ends here. The V sub, just call it V. We got potential V across the ends right there. And yes, I call that L. Good. And I'm calling this potential V0 across the ends. And then we're going to talk about the current and the resistance. So what we have is no current flowing, perpendicular to the surface here. And the typical symmetry argument is going to tell us that we just have a current along that direction. And we're going to have a uniform current, so we're going to have V, and I'm calling this the Z direction. V of Z is just going to be V0 Z over L, so that across the entire length we have that V0 right there. But now we can get E, the electric field, is going to be minus the gradient of V, which is going to be minus V0 over L. So there's our electric field. And since there's a vector, I have to say I've got Z hat. Okay. Good. So now let's go ahead and apply our definition again of J. Going to use the sigma, the phenomenological material property sigma. We've got J is equal to sigma times E. And we have, because of the uniformity in that device, we can just say we have I divided by A, current per unit area. Going to be sigma V naught divided by L, and I'm going to solve for V. Actually, we'll just call this V. So then we've got L over sigma A times I, or V is equal to rho L divided by A times I. And what I have right here is just the resistance. So whether I use 1 over, sigma, 1 over sigma, or rho, conductivity, resistivity is the same thing. Okay. So this is a nice form. And that again, of course, is Ohm's law. In the simple form, the way we first encountered it, V is equal to Ri. And again, we have this expression for R with resistance, resistivity, material property proportional to the length, inversely proportional to the cross-sectional area. Okay. Good. So the next example we want to do is a little more interesting, but we needed this one to start with. So now we're going to consider, I'm writing pretty big here, but a concentric conductor, a concentric cylindrical conductor, and then we'll do a concentric spherical one, and that one we'll put on the homework, so I'll do the cylindrical one, and there's an interesting limiting case on it too. So the next example, now that we have Ohm's law, and we have resistance, resistivity, proportional length, inversely proportional to cross-sectional area, which makes a lot of sense in the idea that this is resisting something. Okay. Yeah, you guys should put some words in with that. I should put some words in with that too, but we're moving on. So the next example is concentric cylindrical conductor. And the idea is now we have radius A, radius B, so A is less than B, and then we've got this length again, L, and here we want to imagine or to figure out what's the current flow, right? We just were able to figure out resistance and current with respect to that. We want to get the current that would flow between these two, the inner and the outer shells, so to speak, material conductivity sigma, if we had current, if we had a potential difference between the inside and the outside. So find current I if VAB, VA minus VB, or vice versa, we don't care about that. So if we have potential across the outside and the inside surfaces. Across outside and inside. And inside. So that's not quite as simple, so we have to do a little bit for it. So what we're going to do is invoke the symmetry of the thing. And we'll get the E field, and then we'll get the potential. So first step, find the E field per unit length. Find E. So we've got the symmetry here. When we're using Gauss's law, if this thing is sufficiently long, we're ignoring the ends, and we're just doing a Gauss's law around part of the middle here, okay? And based on the symmetry, we just have a field that's radially out from that cylindrical body. So here's what we have. Using Gauss, first of all, we'll formulate it. E dot D area is equal to the enclosed charge divided by epsilon naught, so Gaussian surface. And we're just going to let S, I should have drawn that here, we're going to let S just be a radius between A and B. So I'll write A less than S less than B. And then the area element is surface area of that, and also surface normal directed outward. So these can be trivially dealt with, and right underneath here I'll write 2 pi s times L, that gives us an area, times E. Okay. So E 2 pi s times L, because of the E and dA are parallel to each other. Okay, so we get that. Now the enclosed charge is going to be a constant linear charge density times L, so that's going to allow us to cancel the L's, divided by epsilon naught, and now we're going to solve for E. So E is equal to, L's cancel, E is equal to lambda over 2 pi epsilon naught S, 1 over S, and if this is a vector here, I'll go ahead and call this S hat. Okay, pointing away from this. So there is our electric field, and now we want the potential. But that's just a line integral. So we'll do that. So next, V is equal to minus A to B E dot dl. And again, this could be just as well be the ds that we have over there. It's going to be parallel to E, and so this is going to be trivial. Pull out there. We'll have the lambda over 2 pi epsilon naught, comes out as a constant. Then we have the 1 over s ds. So integral ds over s a to b, and we get lambda 2 pi epsilon naught natural log, the minus sign here, b over a. Switch the minus to a plus. Okay. We've got that. Now we also need to get the current. Finally, we're going to have I is equal to integral J dot D area. And again, the current, I should have put this in my picture. We're talking about the current flowing radially from the inside to the outside, just to remind us of that. So, where are we here? Yes, we want that J dot dA. We've got on the one hand sigma lambda 2 pi epsilon naught S. Now the S hat D area, because these two are parallel, we're just going to get S times the circumference times the DL and the width. Okay. So that's why the 2 pi S here and the 2 pi S from this integral cancels. And we're just left with sigma lambda L over epsilon naught. So yeah, you gotta be careful seeing what I did right there. The S hat pointing out the dA is as well. So they're parallel. We're getting the 2 pi s out of the numerator and the denominator. So that's what's left. And now we can put these things together. And what we're going to do, we have a lambda here, and we have a lambda here. We know nothing about those, and we're actually just going to cancel. And we're going to make a substitution for the lambda out of these two and see what happens. So, got this result. So let's call this star and this double star, and we'll eliminate lambda from these two expressions. Okay, let's see what we get here. We have, actually, what are we after? Actually, got my stars wrong here. These two are the ones we're going to compare. Same thing, eliminate lambda. Eliminate lambda, star, double star, and we'll see what comes out. We can have I is equal to sigma L over epsilon naught. Sigma L over epsilon naught. We want to get the lambda from up here, which is V 2 pi epsilon naught over natural log B over A. Good. Epsilon naught. And in fact, we're going to solve this for V. We'll put it in the Ohm's law form again. So V equals Ri. So we're going to solve for V equals that's right. V equals log B over A over 2 pi sigma times I. That'll be the V equals Ri. V log B over A 2 pi sigma, L's missing in there, sigma L. Good. Is that what I have written down here? I should. Yeah. Okay, this is interesting too. So now that we've gotten this result, of course we want to analyze it and see if it makes some sense. There's our potential difference across, I'm going to draw a picture of this thing again. Just a short cross section this time, A, B, L. And again, it's the current flowing like this between those two. So it doesn't look exactly like the other one. Of course, completely different geometry. But we can actually regain the other result, which will be kind of interesting. So yeah, that's volts, resistance for this strange geometry, and current. So let's go ahead and talk about the limiting case. And see if we can regain our other expression after all. Okay, so there's the geometry. I should get this all on one board. There's the geometry. This is the proportionality constant resistance for the current that's doing what the red arrows are showing. First thing I'm going to do is we're going to write it like this. V is equal to rho log B over A 2 pi sigma L, okay, times I. In the limiting case we're going to do, is B minus A, so let B minus A be much less than A, which means we're looking at something like this on it, okay? So a thin shell instead of, general case. Then we can do an interesting expansion. Then natural log of B over A is equal to the natural log of A plus B minus A divided by A, which is the natural log of 1 plus B minus A over A. And the approximation for natural log of 1 plus something small is just this expression here, the first term in the Taylor expansion. So that would be approximately B minus A divided by A. So this gives us an interesting expression. Now we have V equals the rho here. This natural log of B over A is now turned into B minus A over A. And then we have, got a mistake here, but we caught it. It's either sigma or rho. Very good, right? We had 1 over sigma, therefore we had rho right there. Okay. Caught that. So our rho, B minus A over A, we've got the 2 pi, and the L, bracket that again, times the current. And what we see here is the resistance is, of course, the resistivity times this length divided by this area. Okay. In this case, since the current is flowing, let's say just from inside to outside, B minus A is a length, so B minus A, and then the 2 pi A times L is that entire surface area essentially, because B and A are very close together. So that turned back into rho length over area of our original long wire version. So yeah, we're always trying to do these kind of limiting cases whenever they present themselves, because it's a good way to check a result, for its real plausibility. So that's a good consistency check. That's exactly what should happen in a situation like that. It just happens to have been wrapped around into a circle or into a cylinder. Okay, let's have a look here at the time. So what I'm going to do next is set up a couple of homework problems. I'll put together a list of things that we want to do. Good, so we got our limiting case right there. So the next thing is just to talk about a couple of homework problems, and I'll get them going. So we'll just call this example homework problem, and this is 7-1. 7-1 out of our text. So let's see what we have there. So that is very similar to this problem, except it's going to be concentric spherical shells instead of cylindrical shells. So we have concentric spheres A less than B. And you know, I'll just do the cross section because we've got the A, the B, and we've got the materials property sigma in the shell itself. So to tackle this problem, you can start with the electric field being, say, QA over 4 pi epsilon naught unit vector over r squared. We know that from Gauss's law, from symmetry, that that's what it has to be. Whatever the charge is on the inside, this is all the way for A less than R less than B. Okay, so we use that and then calculate V VA minus VP. Okay, so that's just a line integral, radial this time, you know, like that. Okay. So yeah, just like the one we did. VA minus VB, what next? Again, use I equals integral J dot D area to calculate R. Again, same thing we did, and by symmetry we know the current's going to be just radial, like that red arrow is around the entire thing as well. Etc. So there's a few other things asked for, but that's how you get started on the problem. Okay. Concentric spherical shells, work your way through it like that. So next we're going to go to a simple circuit and talk about power. So we have Ohm's law already, and we want to talk about power and joule heating, and then set up a simple circuit problem as well. Okay, so this is power. And we know we can say it's work over time. So that would be using a chain rule type of thing, work per charge, actually just a dimensional argument, work per charge, charge per time, which is nice because then we have your power equals work per charge is V and charge per time is I. And if we have V equals Ri, with Ohm's law, we get P is equal to Ri squared. And that's joule heating. Right, we were talking about the friction, or the friction in scare quotes, because of the collisions, whatever's going on inside the material that keeps the charges from accelerating as a whole. Okay. And there's the expression for the power that is generated under those circumstances. So yeah, let's go ahead and hold on to this. Got it straight out of here. And the example we're going to work is a simple circuit. Consider the following circuit. And we're going to, this problem actually, this is problem 7.2, so 7.1 up there. So I'll even start this up now. Homework problem 7.2. Okay. So there are two circuits. The first one is just if you discharge, we've got Q, across a resistor. So you've got a capacitor and a resistor. And say you had charged capacitor, you had a switch here, and then you close the switch. Close the switch. Here, I'll just put it. Close the switch. Close the switch. What happens? So what we want to do is close the switch and then calculate the current that flows through the circuit. And that has us solving a little differential equation, so that's interesting. So for that we need a law or definition of the capacitor. And then we have Ohm's law, and we should be ready to go. So we have a closed switch, what happens? We have let me check this before we move on. Yeah, we're doing that first. Problem 7.2. Yes, homework problem. Good. Close the switch. Here's what I have here. At t equals 0. So yeah, it's a time-dependent problem. So we have Q equals C times V. And we can even say V naught because that's the full charge. I'll just write CV. But yeah, that's the full charge in the original voltage across the capacitor. And we have V equals Ri, so we'll make a substitution. Q equals R times C, those are our two constants of the problem, times the current. And I'll go ahead and make my substitution next here. And dq dt is going to be minus I. So we're going to have the minus sign here because the charge is decreasing when we close the circuit there. Because Q decreases. So yeah, we can turn that into a differential equation. So we have Q equals minus RC dq dt, and then we'll separate variables. We'll have dq over q on the one side is equal to minus dt over RC. And you know, that's enough. I've set that thing up for you. And I'll just write find Q of t and I equals dq dt. So you get those two, you get these two results. And it gets interesting after that. So next, we'll have to consult what's actually in the book. But if you want to get the total work, or the energy, you know, you've got power dt from 0 to infinity. I forgot what we're calling it, work or the energy, but it's the total energy expended. And you're going to have your power, you'll use your Ri squared, and you'll use the I equals dq dt squared in there to do these kind of calculations. So that's interesting. And I just have what we're going to end up with here, what I'll end with. Yeah. So I'll just write here, oh, the second circuit is going to be charging a capacitor and charging a capacitor using a battery where the circuit also has a resistor in it. So that's a second problem, very similar to this one. And when you do that, you'll get to part D, where you're finding that the amount of energy used to charge that circuit, not this one, but the one with the battery in series, is going to be 1/2 of it will go to the capacitor, 1/2 of the total energy, the other half got burned in the resistor in the process of charging it. So that's an interesting result. I'll write that down so you know what you're shooting for. So for part D, show that energy sub resistor is 1/2 C V naught squared, and energy sub capacitor is also 1/2 C V naught squared. Right, the energy in the capacitor is stored there once the thing is running. And actually, when time, as time runs out, the current stops flowing, and you've got the same voltage drop across the capacitor that you have across the battery. Okay. So 1/2 of that energy, using this type of calculation, using that type of thing there. 1/2 of the energy is burned in the resistor, 1/2 stored in the capacitor. Good, that's as far as we're going to get today. I'm going to write up some remaining problems. And use this section of the board. So I actually looked up a fair little collection, and here's what we'll do. Homework number 1. So these are the chapter 7 problems, and I wrote down a fair collection, I think I did. Yeah, here. So problems, and I've set these up already. So 1, 2, I've set up, but then I added a big list here, 3, 5, 7, 8, 11. Next lecture, I'll actually trim this back and see how many of these are due this Friday. Not necessarily all of them, but I looked at them all. There's a collection. So, definitely these 2 and a couple more, who knows, maybe the first 5 or so, would be due this Friday, but I'll tell you more about that next Thursday, depending on how far we get. Okay. Okay, so how's that for definite? Okay. Definitely maybe. Again, there's the list for homework number 1, but however, how many of them are actually due on Friday, we'll decide in the next lecture on Thursday. Okay, good. That's it for today. We'll see you guys next time.